We shall now proceed to describe quantum effective action, as I mentioned earlier. But before that, before I directly introduce quantum effective action, some tools have to be developed, and that's called one particle irreducible diagrams. So I will begin my discussion with that one. One PI diagrams. We are considering tadpole-free theory. If there are tadpoles, we get rid of this. We get rid of that by shifting the field, as I have described in previous lecture. Then consider endpoint amputated Green's function. We are considering connected Green's function. And that's given by A tilde n connected P1 to Pn. Now consider all possible diagrams, all the diagrams in this, and then divide it into two parts. One, I tilde n so these are all connected. I will not write C explicitly here. P1 to Pn, and then I tilde n P1 to Pn slash. Now, what are these two sets of diagrams? This is one particle irreducible. So that will be denoted as this. There are a bunch of external lines which are all amputated. And this one I will denote as 1 pi slash not 1 pi. These are these are not one particle irreducible diagrams, and these are of course amputated. Now, what is 1 pi? So these diagrams are such that the diagram does not get disconnected if an internal line is cut. Okay, that's the definition of one particle irreducible diagram. So let's look at some examples. Let's take A tilde 2 connected P1, P2. That will involve, so basically we are talking about this diagram. This is a connected Green's function, but with amputation. The first one will be propagator, which is amputated. And then the second one is a one loop diagram with amputation. Then one has this one. You see in this diagram, in the second diagram, this is the only internal line. If you cut it, the diagram does not get disconnected. So this is a 1 pi diagram. In this diagram, if you cut here, then of course it gets disconnected. In fact, this diagram should not be there if there is no tadpole. So I should not draw this diagram. So I remove this. Then you have a diagram like this. This is 1 pi, because there, if you cut any of these internal lines, this one, or this one, you cut any of them, it will not get disconnected. Similarly, this overlapping diagram, this is also 1 pi. This is again, let me not draw that. This one is not 1 pi, because if you cut this line, then it will be disconnected. So these are some examples of 1 pi diagrams, 1 pi and what are not on. So we take these as not 1 pi, the first one, because there are no internal lines here. We just define it to be non 1 pi. Then one can convince oneself easily that these, if you collect all these 1 pi diagrams and non 1 pi diagrams, then must be having this type of a structure. So this diagram, my claim is that can be written as that is obviously true, but because these tadpole diagrams are not present, this non 1 pi part will have the following structure. It is like this. And so on. Basically, the 1 pi part is going to repeat is going to repeat, and that's like a GP series. Now, if this is, let me denote this by 1 over I pi p square, where p is the momentum that is going in, right? This is p1 p2, but because of there will be an overall momentum conserving delta function, which is p delta p1 plus p2. So let me call p1 as p. So p coming in and p going out. Those external line propagators are amputated, but nonetheless, this object does depend on p, and in fact depends only on p. All the other internal lines are either fixed, have momenta which are either fixed in terms of p, or they are integrated over. If this is the case, then this will be pi 1 over I times pi p square. Then if this is p, then one should have a p flowing here, so that will be 1 over I delta tilde p and 1 over I pi of p square. So there are two factors of 1 pi, and therefore there are two factors of pi connected by a line. Here there will be three factors of pi and connected by two lines. So that is how it is going to repeat, and it looks like a GP series. So let us calculate the connected Green's function. So if you consider connected Green's function, G tilde C, let me call it P. Basically, what I'm saying is that this corresponds to this diagram, the connected diagram. Sorry, this is not G tilde C of P. So this corresponds to the connected diagram, connected two-point function, which is basically obtained by taking the amputated diagram, this one, and attaching the two external lines, right? And therefore, this diagram should correspond to the following series. The first line, the first one in this A, which was this line, that was amputated. Now it will have a propagator because I'm connecting the external legs now. So the same series that I was drawing earlier, but now with the external legs. So then that expression, the corresponding math expression, will be 1 over I delta tilde P plus 1 over I delta tilde P pi 1 over I pi p square plus, okay, times 1 over I delta tilde P 1 over I delta tilde pi, sorry, 1 over I pi, then 1 over I, another delta tilde, 1 over I pi, and then 1 over I delta tilde. So there are 3 propagators and 2 factors of pi's. So this is 3 propagators and these 2 factors of pi's. Okay, this is how it will proceed. If you take 1 over I delta tilde out, you will get 1 plus 1 over I pi times 1 over I delta tilde. Then in the third term, this has been taken out. So this is 1 over I pi times 1 over I delta tilde. And this is the same factor. So it is square of that. 1 over I pi 1 over I delta tilde square. And so on. So that's a geometric progression. And we can use the formula which is given by this 1 minus the ratio is this. So 1 by 1 minus 1 over I pi times 1 over I delta tilde. And then you can divide it in the downstairs. So that will be I times delta tilde inverse minus minus, so this divides, so this is going to divide this one, so we'll get rid of this, and minus 1 over I will become plus I, so that is plus I pi. Now what is delta in delta tilde? Delta tilde is 1 over p square plus m square with I epsilon prescription or Euclideanization. Therefore, the delta tilde inverse will be p square plus m square. So it is 1 over I 1 over p squared plus m square plus pi of p square minus I epsilon. So this is the form of the entire 2-point function, connected 2-point function. This is the 2-point function, but then there are interactions, there are loop corrections to this propagator, and this after correcting all of them, this is the final form. This is the exact propagator, and this can be viewed as correction to the mass square due to the self interactions. So this is an exact propagator. It's called self energy contribution. So so when I write an arrow here like this, it means that this is not same as this, but it has this 2 pi to the power d times overall delta function, overall momentum conserving delta function, g tilde times that is this diagram. So that is what I calculated here. So there will be a 2 pi to the power d factor. The overall momentum conserving delta function is already taken into account within the diagram. So that is what I calculated. So I just wanted to explain what this arrow means. Here also I am supposed to have 2 pi to the power d delta p1 plus p2. If I had written that, then it will become an equality here. Now this is about the 2-point function. So let me so this is n equal to 2. Now let's go to n equals 3. In n equals 3, a tilde 3 connected p1, p2, p3. Times 2 pi to the power d times delta p1 plus p2 plus p3. If you calculate this, then you get these diagrams with amputation. P1, P2, P3, all incoming, and then of course this is 1 pi, this is also 1 pi. But then if you draw this diagram, then this is not 1 pi. This is again 1 pi, and this is not 1 pi, and so on. Now, if you write, if you write this all this full set of diagrams as in this following form, that 1 pi plus non 1 pi then the question is that what is the form of the non 1 pi diagrams? Just like we are attacking the question the same way as we did for n equal to 2. And as you can easily convince yourself, you see this whenever the vertex itself is resolved into certain loop, certain sub diagram involving loops. There are when you draw such diagrams, there are two broad topological categories. One is that this vertex is being replaced by certain loop diagrams, this one, and the other is that the vertex vertex can remain same or be replaced by certain loop diagrams, but the legs can also have certain loop loop corrections. Anywhere in the first category, if you cut a line, then the diagram will not be disconnected. But here, in this case, the diagram will be disconnected. So in the first category, topological diagrams will all go into this one. And therefore, the second one are basically whatever the 1 pi diagrams for 3-point function is, you have additional leg corrections. for each leg you have additional corrections. Now, so that means it must look like so when you add all of them, it must look like where this is the 3.1 pi and this is the connected 2-point function that we just calculated here. Let's not continue. Let's now continue the second one.